Everybody grab a seat. I also want you to start doing lots of homework now, because the next topic we're going to be looking at is as follows. We're going to be looking how to solve now non-homogeneous, in other words, second order linear ODEs with a given right-hand side. In general, we'll be looking at the case where this coefficient, and this coefficient, this g of t, are all continuous in some interval, I. The homogeneous problem that goes along with this one, with g of t on the right-hand side, is the one where you have 0 on the right-hand side. And the first thing I'm going to show you is what's the connection between solutions of this with the 0 and solutions of this with the given right-hand side. Okay, so the first thing is observe. If y1 of t and y2 of t are solutions of 6,2, okay? In other words, y1 and y2 are solutions of this equals g. Then, oh, sorry, 6,1, the first equation. Then, the difference, y1 minus y2, solves 6,2, the homogeneous equation. Now, we could go through and write down that as a proof, but it's very easy to see, so we'll just talk our way through it. y1 satisfies this equals g. So I have d2 y1 by dt squared plus p of t dy1 by dt plus q of t y1 equals g of t. I have the very same equation for y2. I subtract the two equations. And what am I going to get? I'll get d2 by dt squared of y1 minus y2 plus p of t times d by dt of y1 minus y2 plus q of t times y1 minus y2 equals g of t minus g of t, which is 0. Okay? So, the difference of any two solutions of the inhomogeneous equation, 6,1, the one with a non-zero g of t, satisfy the homogeneous equations. Now, this lets us devise a scheme for finding the general solution of this guy. By general solution, I mean one with enough degrees of freedom that I can satisfy arbitrary initial conditions given on the value of y at a time t0 and its first derivative. Excuse me. I had an urge there just to keep on going. Anyway, so the recipe for getting the general solution of 6,1. Okay, now let y of t be the solution of 6,1 which satisfies the initial conditions. I'll push this board up in a moment. I just want to write one more line here. Let yp of t be a solution of 6, 1, which may or may not satisfy the initial conditions. Right. So, I say let y of t be a solution of 6, 1, the one we want, which satisfies the initial conditions. Yp of t is just any old solution of 6, 1, whether or not it satisfies the initial conditions. For instance, let's look at this example over here. Okay? The solution that satisfies these initial conditions is not that complicated, but it'd be impossible to guess. But can you guess a particular solution to this equation just by looking at it? The solution does not have to satisfy the initial conditions. It can satisfy any initial conditions. What would be a possible solution of that equation? It's a very simple one. Very good. Y equals a half. See that? So in this case, our yp would be simply a half. All right? Now, y of t, the solution we want to satisfy the initial conditions, now we will construct using yp. Why? Because what do we know about y minus yp? Y and yp, yes?
Did you say y of pt is equal to 1/2?
Just in this case, yeah. See, because y equals 1/2, that cancels that. Y prime is 0, y double prime is 0. Now, what do we know about the difference of those two solutions? Yes? It solves 6-2. So this satisfies the homogeneous equation. So it solves 6-2. So let y1 of t, y2 of t be two linearly independent, Li, linearly independent solutions, and their Wronskian, of course, will be non-zero. Solutions of 6-2. The general solution of 6-2 is ay1 plus by2. But y minus yp of t satisfies 6-2. So we have y minus yp of t equals ay1 of t plus by2 of t. In other words, the general solution, y of t of 6-1, is the sum of any particular solution of 6, 1 plus the general solution of 6, 2. So y of t is some particular solution plus a y1 of t plus b y2 of t. So that's our recipe. What we'll do when we're faced with solving 6, 1, we will first solve 6, 2, and we've already learned methods how to do that. We'll find its general solution. Then we chase after one particular solution of 6, 1. Doesn't have to satisfy the initial conditions. Then the general solution will be this particular solution plus this linear combination. Now, because y1 and y2 have non-zero Wronskian on the interval, we can satisfy any two initial conditions that we care to give at a point t0 on this interval. So the initial conditions would be y of t0, which is gamma naught, would be y of p of t0, which we know because it's a particular solution, plus a y1 of t0 plus b y2 of t0. And y prime of t0 is gamma 1, which is y prime, yp prime at t0 plus a y1 prime at t0 plus b y2 prime at t0. Two equations for the two unknowns, big A, big B. So, we know this, we're given this, gamma naught and gamma 1. We know this because we've computed a particular solution of 6, 1. We know, of course, these guys. So, two equations, two unknowns for A, B. And for any gamma naught and gamma 1, we are guaranteed finding a solution for A and B because this determinant, this Wronskian, is non-zero. All right, there's the challenge and the recipe. Let's do it for here. You have all the ingredients. Okay? This young lady, sorry, your first name? Marissa. Marissa told us that yp is a half, is one solution. Is a particular solution of the full equation. So the general solution will be a half plus A plus B. Okay? Now what goes in here? Find for me two linearly independent solutions of the homogeneous equation. Y equal e to the RT. You want to solve this equals 0 and find the general solution of the homogeneous equation. Anybody here with a birthday this week? Gotcha. You know, good man. What's the general solution? You're correct in the first one. E to the minus t is one solution. What's the second one? E to the minus 2t. Okay? Because the characteristic equation, if we look for solution e to the RT of this equals 0, I get r squared plus 3r plus 2 equals 0, and that factors into r plus 2 times r plus 1 equals 0. So r is minus 1 and minus 2. So now,
Why were you able to just set it equal to 0 as opposed to 1?
okay, the question is, why were we able to set it to 0?
As opposed to the 1?
As opposed to the 1? Because I've told you that the recipe for finding the general solution to 6,1 is to find any particular solution to 6,1. Then the difference between the solution you want and that particular solution solves 6,2. The general solution at 6,2 means this equals 0. Okay? Question, yeah.
Are there going to be cases when y, p of t is dependent on t?
Yes. The question was, are there any cases in which yp is dependent on t? Of course. Absolutely. You don't get away this easy most of the time. In fact, the basic message of today's lecture, I'm going to be showing you a method to compute yp of t in a large variety of interesting situations. But here I'm just illustrating. Sometimes you can just guess. But in general, you're not going to be able to guess. Okay? Now, to solve the initial value problem, therefore, we have y0 equals 1. And that's equal to a half plus a plus b. And y prime of 0 is 3. And that's equal to, when I differentiate this, the half disappears. I get minus a e to the minus t. At t equals 0, that's just minus a. And then I get minus 2b from here. So you have a plus b is a half, and minus a minus 2b is 3. I think it turns out that if I add those two equations, I get 7 over 2 is, so I think b is minus 7 over 6. And then a would be, if a plus b is a half, it would be what would it be? I want a plus b to be a half. Let me see if I got those right first. Yeah. B is minus 7 over 2 is correct. Yes, that's right. That's better. All right. And therefore A is what? 9 over 2. All right. So now we have the general solution of this problem. Now, as was pointed out, yes, question. Is it? All right. 4 minus, yes, you're absolutely right. How did you know that? That's his birthday this week, so. Good, thank you. It's my birthday 2 weeks from now, so I'll get it right then. All right, so now I have to give you a general method for finding yp of t. Because we have, for at least a broad variety of circumstances, we have a general method for finding solutions of the homogeneous equation. That's the one with g equals 0. Now, if we can find methods to find particular solutions, by combining these two things, we'll be able to get general solutions to the non-homogeneous equation. So, The first method I'm going to teach you is called the method of undetermined coefficients, which is a bit of a misnomer because the whole idea is you're going to determine the coefficients. But anyway, that's what it's called. So, the method of undetermined coefficients. It works, not in all cases. It works when P and Q are just constants, and G of T is a linear combination of functions which can be written in the form t to the m, e to the at, cosine or sine b of t. Where m is a non-negative integer. It's an integer, but it can also be 0. Positive integer, but also 0. We call this class C. We'll call that class of functions C. So, let's think of who belongs to this class. Examples. 1, of course, belongs to the class of functions. M would be 0, A would be 0, and the B in the cos bt would be 0. T belongs. T e to the 3t sine 5t. That belongs. The most interesting ones, we're going to be spending a lot of time, would be these ones. Cos omega t and sine omega t. They're the ones which actually have the applications that we're going to be most interested in this class. Question?
So these are the options we have for m?
No, these are just examples of functions which fall into that class. Like in this case, the m is 0, a is 0, and the b in cos bt is 0. In this case, the a is 0, and the b is 0, and the m is 1. Here, the m is 1, the a is 3, and the b in sine bt is 5. Now, yes, question?
You said the G of t is a linear combination. Does that mean you can add?
Yes, you can take any combinations of these, yes. Now, a couple of comments before I actually show you the method and indicate why it works. The first comment is, I'm going to teach you in about a week and a half a very general method called the variation of constants. It's the more general method for finding solutions for not only second order equations, but actually nth order linear ODEs. And if one can find solutions to the homogeneous problem, in fact, in principle, there's a formula that you can write down for the solution to the inhomogeneous problem. So why do we waste our time on this simpler method, which only works for a special class of functions? The answer is the general method, the method of variation of constants, while being very useful, is also calculationally challenging. You have to know all sorts of things like trig formulae, like cos 2t, cos t, plus sine 2t, sine t, to know what that is, in order to get your answer in simple form. So it's a lot more work, and there's a lot more room for mistakes, and in some sense you see less the wood than you see the trees. There's so many trees in the method that you miss the big picture. And it's very important we get the big picture, because in a lot of examples that we're going to be looking at, we will be solving 6-1, where the P of t and Q of t will be constants, and the right-hand side will simply be cosine and sine of omega t, or combinations of those, because they describe many things that come up in chemistry, like for instance the oscillations of a covalent molecule, which is struck by sort of an electric field due to light. How does the molecule get excited? How does the molecule interact with light? We'll be looking at LRC circuits, how your radio works. Okay? In other words, how do you design a receiver in order that you can discriminate against all the stations that are flooding your area with lots of signals? You want to choose the signal corresponding to the frequency of the station that you want to listen to, and not all the other stuff. And some of the other stuff is sent with much stronger intensities even. So you need to discriminate. In fact, Thursday's lecture is in fact how essentially tuned circuits, LRC circuits, discriminate. How they pick the signal that you want to listen to. Lasers. Lasers also can be described essentially, approximately, by a second order equation, essentially for the dielectric moment, driven by an oscillating electric field, which can be represented like cos omega t. So many of the examples we want to study are those where the P and the Q are simply constants, and the right-hand side is some combination of cosines and sines. So for that reason, this method is quick and easy to apply. So let's learn it. All right. So, step 1. So I'm going to put the menu up here. Okay, step 1. The first step is you find two linearly independent solutions of the homogeneous equation. Find y1 of t, y2 of t, two linearly independent solutions of 6-2. That's your first job. Step 2. You're going to use it in two places. You're going to use it, first of all, to construct the general solution, but you're also going to, it's also going to interact with the further steps that I'm going to write down now. Okay, we form the auxiliary set of G of t. And we call that G of t in curly brackets. Now what is that? It's the set of all linearly independent functions obtained by repeated differentiation of g of t. Now, at the moment, that's all gobbledygook. That's just the statement. I'm going to give you examples in a minute. Okay? I'll give you examples now, I think, because then it'll make the next step a little bit more clear, I think. Okay, so the example. Supposing g of t was t e to the t. Okay. Let's differentiate it once. G prime is what? It's e to the t plus t e to the t. Let's differentiate it again. G double prime is e to the t plus t times e to the t plus I get another e to the t. If I keep differentiating, I never get anything else than either e to the t or te to the t. Repeated differentiation just gives me expressions which are linear combinations of e to the t and te to the t. So the auxiliary set of this guy is e to the t and te to the t. That's it. Now, how about this? G of t is t squared. What's the auxiliary set of t squared? Just keep differentiating. What do you get when you differentiate the first time? Next time? Next time? Next time? So what's the... Give me the linearly independent functions that everything is a combination of. T squared, t, and 1. T squared, t, and 1. Because everything you get by repeated differentiation of g can be written as a combination of t squared, t, and 1. One more. G of t is cosine omega t. What's the auxiliary set? Yeah? Get sine, and when you differentiate sine again, you get, and then differentiate again, and again, and again. So what is the base, what is the two linearly independent functions that every derivative is combination of? Sine and cosine omega t. Right, so that's step 2. Step 3. Step 3. Modify auxiliary set if necessary. Okay? If any member of the auxiliary set that you just computed of g of t solves 6-2, in other words, is a solution of the homogeneous equation, whose solutions you've already determined here, then multiply each member by t to the m, where m is the smallest integer such that the modified auxiliary set contains no solution of 6-2. Yes?
So you have to multiply the entire set by 2.
Yes,
not just
the entire set corresponding. And we call this g of t with a stroke over it. Now, rather than do examples here, I'm going to be doing examples shortly, and you'll see how to operate this. Step 4. You see, yes, question?
Yeah, I was going to ask, how would you know what the smallest integer is if it's something like cosine and sine?
Yeah, we're going to, let me come to an example and then you'll see that.
Okay.
Step 4, you seek yp as a linear combination where this auxiliary set is just these functions here, up to phi r of t. Okay? So in other words, you're going to just shove that in your equation and use what you get to determine A1 up to AR. These are the coefficients which are undetermined before you do the method and which you will determine after you apply the method. All right, so now there are the rules. So now we do lots of examples. Now, on your notes, lectures 11 through 16, on page 5, there are about 10 examples listed, and actually most of them are worked out in the pages after that. I want you to be extremely familiar with all of these examples. Doing example after example will teach you the method much better than just watching me here do it on the whiteboard. So I want to stress this. Homework, homework, homework now. This is the way to learn this method. Okay, now we're going to do some examples. We got all our rules down there, and now we're going to do examples. Okay, example 1. Y double prime plus 3y prime plus 2y equals t squared. And we'll take y0 equals 1, y prime of 0 equals 2. We want to solve that problem. Okay, step 1. All right, birthday boy who's asleep, what are the two solutions of the homogeneous equation? Right, good. y1 of t is e to the minus t. y2 of t is e to the minus 2t. So now we've completed step 1. Step 2. What is the auxiliary set of t squared? Exactly. Step 3. Are any of these guys solutions of the homogeneous equation? They'd have to be combinations of those two. So, what do you think? No. So, no need to modify. Still t squared, t, and 1. Now, step 4. We seek yp as a1 t squared plus a2t plus a3 times 1. Yes, question?
You say why you didn't need to modify?
Because none of these were solutions of the homogeneous equation. Right? Because the homogeneous equation has solutions e to the minus t and e to the minus 2t. So any combination of those is the general solution, and t squared and t and 1 can certainly not be written, right? All right, so if yp is that, yp prime is 2a1t plus a2. yp double prime is 2a1. Now we just suck it into the equation. We suck it in here, and we get what? 2a1 plus 3 times 2a1t plus a2 plus 2 times a1t squared plus a2t plus a3 equals t squared. Now, let me gather the terms together. The terms with no t's in them, I have 2a1 plus 3a2 plus 2a3 times 1 plus 6a1 plus 2a2 times t plus 2a1 minus 1 t squared equals 0. I brought that t squared over to the left-hand side. Now, this is to be true for all t. In the interval on which solutions for this exist, of course, is all t, because there's no, everything is continuous, everything is smooth. Now, so this has to hold for all t. Now, t squared, t, and 1 on the whole interval minus infinity to infinity, are they linearly dependent or independent? They're very different, okay? They're linearly independent. Therefore, if this combination of them has to be 0 for all t in the interval, what can you say about these coefficients? They have to be 0. So, this implies A1 is a half. This implies A2 is minus 3 halves, 2A2 plus 6A1. And then this implies that A3 is 2A3 is minus 1 minus 3 times A2, which is plus 9 over 2, which is 7 over 2. So A3 is 7 over 4. So now my solution is, the general solution is y of t is a half t squared minus 3 over 2t plus 7 over 4 plus a e to the minus t plus b e to the minus 2t. Okay? So that's the general solution. Yes, question?
Yeah, so I see what happened when you took the YP derivatives and put them into the original non-homogeneous equation.
Yeah.
What happened going down along?
Okay, I just collected all the terms t to the 0, t to the 1, t squared.
Oh, so that was just a rearrangement?
A rearrangement, yes. Now, what you can do is, look, just equate, on this equation, you can equate t to the 0 on both sides. So t to the 0, you get 2a1 plus 3a2 plus 2a3, and there's no t to the 0 on this side, so that's 0. The coefficients of t on this side, 6a1 plus 2a2, 0. T squared, 2a1 equals 1. So you can bring them all to one side or just equate the coefficients of the different powers of t, because you know they're linearly independent. Yes?
So was your reasoning for finding the coefficients A1, A2, and A3, did you just kind of set each part equal to 0?
Yes, I set the coefficient of t to the 0 equals 0, the coefficient of t to the 1, 0, and the coefficient of t squared, 0, because that expression has to hold for all t. And it won't hold for all t if the coefficients aren't 0. So this is the general solution. Then you determine A and B simply by putting in the initial conditions. Okay? Yes, question?
Can you explain how you know the coefficients have to be 0?
Okay. So supposing I told you the following. Supposing I say, okay, A plus BT plus CT squared, I'm going to demand that you make that 0 for all t between minus infinity and infinity. Okay? Now, is that possible? Well, it's certainly at one particular t that solves that quadratic equation, it'll be 0. But it has to be true for all t. Is that possible? No, because t to the 0, or 1, t, and t squared are linearly independent functions on that interval. And linearly independent functions are such that if you take k1 of one of them times k2 of another, k3 of another, and make that 0, the only way that that can hold throughout the interval is that the coefficients have to be 0. Question, yes?
You have to wait to solve for A and B until that very last step?
Yes, yes. You don't solve for A and B at the beginning by just using the homogeneous solution. Good question. So you wait, you get the general solution like this, then solve for A and B. All right. Part number 2. Okay. E to the minus t. Okay, step one. Step one.
Excuse me,
Yes.
could you explain step 3 one more time?
Step 3 here. You're going to see it in action. So, I shall be calling on you. All right. Step 1. What are the solutions of the homogeneous equation? It's the same, because same left-hand side. All right, step 2. What is the auxiliary set of e to the minus t? You just keep getting e to the minus t. Differentiate once, twice, you get minus sign, then the minus squared, minus cubed. So it's just e to the minus t. So there's only one member of this set. Now, does this guy solve the homogeneous equation? Yes. So now I have to modify this. First of all, I'll multiply it by t to the 1. Okay? T e to the minus t. Does this solve the homogeneous equation? No. Okay? So now I stop. There. Question.
Why did you just decide to multiply by t?
The rule is I multiply by the lowest power of t so that each member in the auxiliary set no longer satisfies the homogeneous equation. The lowest power of t, yep.
And you just use the right-hand side of the equation to get step
Yes.
right?
Yes. Yes.
So you're just allowed to like disregard negative e to the negative t, right?
Yes. Negative e to the, it is a linear combination of e to the minus t. You want to get all the possible functions you get by repeated differentiation and look for the bases, the set in which you can describe every function as a linear combination thereof. All right, step 4. We seek y of p equal a1 t e to the minus t. Okay, yp prime is a1 times e to the minus t, 1 minus t. Because when I differentiate the t, I get e to the minus t. When I differentiate the e to the minus t, I get minus t e to the minus t. yp double prime equals, excuse me, minus a1 e to the minus t times 1 minus t. Then the first times the d of the second, which would be minus a e to the minus t. Okay, so this is equal to t e to the a1 times t e to the minus t minus 2a e to the minus t. I need a 1 there. Okay, now suck it into the equation. So I get a1 times t e to the minus t minus 2a1 e to the minus t plus 3 times a1 times e to the minus t times 1 minus t and then plus 2 times t e to the minus t. And that's got to be equal to e to the minus t. It's 2a1, yeah. Mm-hmm. Ah, yes, thank you very much. Plus 2a1. All right. Now, these expressions, there are two essentially different functions. There's e to the minus t, which appears, say, in this product here, and this te to the minus t. Now they're linearly independent, so the coefficients of each have to match both sides. Or if we bring everything to one side, they have to be 0. But how many constants do I have? 1. But I have to match 2 things. I'm going to have to get lucky. Let's check. te to the minus t. So I get this term, a1. Then I get minus 3a1 from this term. And then a plus 2a1 from him. I didn't need him. And this happens simply because e to the minus t is a solution of the homogeneous equation. So you will always have the right number of constants, even though at the beginning it didn't look like it. But because e to the minus t satisfies the homogeneous equation, the coefficient of this guy will go away. Coefficients of e to the minus t. This guy, minus 2a1. This guy, plus 3a1. Nothing here, and on the right-hand side, 1. So this tells me that a1 is 1. So the general solution of this problem is y of t is te to the minus t plus ae to the minus t plus be to the minus 2t. Yes?
So the number of coefficients you end up dealing with ultimately matches the number of members in your auxiliary set B of t?
Good question. It does, except, yeah, yes, you're correct. Okay. Now, supposing I was to do this guy. The thing is, just do them separately. And add the solution at the end. Add the particular solutions. So get the particular solution for this and the particular solution for this. And just add them here at the end. So what was the particular solution? It was a half t squared and da-da-da for the t squared on the right-hand side. So you do them just separately and just add the particular solutions. Yeah. All right. Another one. So, y double prime plus y equals cosine t. All right, first job. Find the solutions of the homogeneous equation. Find the solutions of the homogeneous equation. So what's the characteristic equation here? R squared plus 1 is 0. So what are the roots? I and minus I. And what are the two real solutions corresponding to those roots? The complex roots are e to the it, and the complex solutions are e to the it and e to the minus it, but we want real combinations of those things. What are the real combinations? Cosine t and sine t. Okay? So y1 is cos t, y2 is sine t. Step 2, the auxiliary set for cosine t. What is that? Cos t and sine t. Right? Because any further differentiation, you just get back cosine, sine, and so on. Do I have to modify? Green t-shirt. Do I have to modify? You don't sound sure.
Yes.
Yes, this is right. Because both of these are solutions to the homogeneous equation. So I have to modify by choosing the lowest power of t. So I try first t. So t cos t, t sine t. Are they solutions of the homogeneous equation? No. So I've finished. Don't have to modify again. If they were, I'd have to multiply another t in. Okay, so now I seek solutions. Yp is a1t cosine t plus a2t sine t. So yp prime is a1 cosine t minus a1t sine t plus a2 sine t plus a2t cos t. Yp double prime is minus a1 sine t, and I'll get another one when I differentiate that. And then I get minus a1 cos t. So that's the d of these first two terms. This one is plus a2 cos t. This one I get another one because when I differentiate the t, and then I get a minus a2 t sine t. Yes. And yes. Thank you. Who said that? Very good. Because I'd have been in real trouble in a moment if I didn't get that. All right, so now I bung it into the equation. So I get minus 2a1 sine t minus a1t cos t plus 2a2 cos t minus a2t sine t, and that's all got to be equal to cosine t. No, I have to add plus y, which is a1t cos t plus a2t sine t. So this is the yp double prime, and this is plus yp, and that's got to be equal to cos t. Now we have four possible functions which are linearly independent. We have t cos t, t sine t, cos t, and sine t. So we have to match them all. So the t cos t, what do I get? Minus a1 plus a1 equals 0. Good. T sine t. Minus a2 plus a2 equals 0. Good. That's scrams. Cos t. 2a2 and nothing here, and just 1 on the right hand side. And sine t. Sine t is minus 2a1 equals 0. So a1 is 0, a2 is a half, And so my particular solution is yp equals a half t sine t. And then the general solution, I have to add this. So the general solution of this equation is this. Now, yes, question.
What are you doing when you say this t cosine t equal 1?
Oh, what I'm doing is I'm taking this equation, which is to hold for all t. I'm taking all the coefficients of here t cos t. T cos t appears here, so I minus a1, and here plus a1. So that's 0. Because there's 0 on the right-hand side. There's no t cos t on the right-hand side. I'm just equating coefficients of t cos t both sides. Then in here, I'm equating coefficients of t sine t on both sides. Here, I'm equating coefficients of cos t, and here of sine t. Question?
Why did you choose t sine t?
Oh, because I found a1 was 0. We looked for a solution like this. a1 we found to be 0, and a2 was a half. Right, now take a look at the solution. It's very interesting. Look at the solution. If I draw its graph, after what's going to happen? It's this sine t is multiplied by t. So it'll go something like this and get bigger and bigger. The envelope of it will grow like time. Okay? This phenomenon is called resonance. You have the natural frequency here, namely the number here, which is 1, and is square root, because the general solution is, if you had a q here, it would be cos root qt and sine root qt. But the oscillation frequency of the homogeneous problem is driven by a force with the same frequency. So it's like pushing the kid on the swing. The kid is swinging like this. And then you give him a swing nudge every period. So he starts swinging higher and higher. And here he is. Here's the swings. So this is going to be very important. Last thing today, and this is important because it's going to be on your quiz tomorrow. I will be asking you, this is in preparation for Thursday's lecture. Stop putting away the books. To draw the graph of this guy. 1 over z of omega. And I'm going to have it like this. It's omega minus 1 over omega all squared plus a very small number, I call it 0.1 squared. I want you to graph this guy as function of omega. Okay? Now, on Thursday's lecture, we're going to discover that this guy, z of omega, is simply the complex resistance in the circuit. In the circuit described by the equation we'll be looking at. This will be the resistance. The capacitance and the inductance will be in this expression. And this guy is called, does anybody know what it's called? Electrical engineers? Sorry? The whole thing is the impedance. You're correct. The z of omega is the impedance, the magnitude of the impedance. This part is the resistance. Do you remember the term for this part? It's called the reactance. So what matters, what we'll find matters, is the difference this actually records the difference between the forcing frequency and the natural frequency, basically. We'll see that in the example I do Thursday. So this is the difference between the forcing and natural frequency. This is simply the resistance. So this is the impedance. So we'll see you Thursday.